need of data from these. So it's an interesting approach comparing how much data we can get from the human and maximizing the performance of the device. So it's a different approach, perhaps, than what has been done before. So this is covering some dissertation work performed by a student named Seth Donahue, who is here. So he's in his third year of doctoral training in our department and comes from a mathematics and applied statistics background within an exercise science master's program. So has some mathematical modeling background, some neural network programming experience before coming to us, and then also has worked with athletes in sprinting performance with prosthetic devices as well. So one of the things that we question is that there's so many ways that limb loss can occur that every situation is not as predictable as far as what the function of the limb is after the injury and after the repair. So these are due to wartime injuries as the most common, perhaps motor vehicle accidents as the second most common for trauma. And then there's vascular complications from diabetes probably impact more people than both of the trauma cases together. But it's a very different sample of humans, right? So instead of the first two involving more of the younger cases of humanity who maybe are in a war experience or driving their motorcycle a little bit too aggressively or something, or taking risks, essentially, they're more prone to potential trauma. Someone has acquired diabetes or that has developed in their condition, then this vascular condition will produce situations that lead to an amputation based on injuries that they were not able to control. So this is a very different case. But the older individual with diabetic complication, they may want to just be able to walk to the grocery store or to play with their grandchildren. And so it's very different design parameters for prosthetic feet. But right now, it's all the same feet being prescribed to the same people, with a few exceptions of the elite athletes getting very nice running devices, and the rest of the population getting essentially what is the most affordable and still functional, but maybe it could be more functional. So then the other cases of limb loss involve osteosarcoma, which sometimes can happen in childhood as well. We have a lot of childhood bone cancer cases that lead to amputation, and this can happen very early on. Luckily, it's something that if surgically affected by an amputation, oftentimes these cases, they have a very long, fruitful life, but they may lose their limb at the age of 2 or 3. And so this is something that they have to adapt very early as to how they get around on a prosthetic device. And so they have different motor patterns that they've learned and adapted to for a long period of time before they have the opportunity to have a prosthetic foot that's robotic, perhaps. So we have, across these 4 cases, a wide variety of historical passive elements in the prosthetic foot. And so we're curious what will happen if you give them a fully powered device or a device that's capable of adapting its stiffness parameters. Will they even know how to use it? And so this is a big question about motor learning, is how adaptable is a human to learn how to use a device that's more capable than what it used to be. So if I have a car that has 1 gear, and I just drive the 1 gear car slowly everywhere, and I do that for 30 years, and then I'm given a Maserati that has a lot of gears, and they're very powerful gear ratios, and suddenly I have a car that I don't know how to control. Maybe I'll get in trouble with that car, right? Run it into a pole or get a speeding ticket or something. But I can adapt to that car, potentially, but I can adapt to it more easily if I learn at a younger age or if I have less complications. So these different cases will have a variety of complications that go with them, whether it's a nerve injury that doesn't allow sensation to occur, or a nerve injury that doesn't allow the musculature to fire the way it used to, or other trauma-related events that make the biomechanics just different for that individual. So some of the solutions that have come out, kind of a J-shaped system here with a cantilever beam underneath for the heel. And so then this whole system for this heel component osmosis fits nicely into shoes, right? So if you put this device right here into the shoe, it won't conform to the shape of the shoe very well. Foot or there. Then there's the argument that maybe they have too much bone to that space. So you can have a relatively simple ankle joint in this case, and also have some shock absorption. And incidentally, this foam is cut in a way that basically provides rollover, and this allows basically a different inflection point or a different point where the deflection in this device will occur. So this is a way for us to vary the functional stiffness of the foot itself. So we're not changing any torque back in here. We're not changing the durometer of anything inside the foot. We're to adapt to this foot that has a variable stiffness pattern. The other thing that's nice about this design is it's not intended to power the human at all. The only power that's required is enough to drive this fulcrum back and forth. And we do that during the swing phase. So when the foot is in the air, there's no resistance. So that's a nice.
So you said that in this shoe, there is the function is similar to rocker shoe. But for rocker shoe, the shape of the shape at the midfoot at the middle arc is a curve one.
Yes.
So how do we achieve this over here?
Yeah.
If we see this, there is no curve in the medial arc.
We don't think that there needs to be a full stage here. The person is basically just C-spine over a bridge, right? Yes. And we think that actually there needs to be a functional bridge mechanism between the two rocker shapes. So you can have a rotation from here to the ground, progression. The foot flattens out, and then until I load it enough, it doesn't roll over the toe. Whereas the full rocker shaped shoes, once the person has enough momentum, they can just kind of coast over the top of it. So we don't think that's quite the best design. Yeah, it's a good clarification, though. And it's not. We don't think that we have the only answer there. I should start thinking that we don't think it's necessary to have the full shape underneath. And then the more of that you can cut out, the mass you're taking away as well. Heavy, but any savings of mass makes the energetics of the human walking more economical. So that's a good question. So there's been other work. This isn't going on in our lab or with our collaborators, but there's been a lot of work in the US recently with exoskeletons and exosuits. So this is something where, in addition to the human, you explain the torque produced about the joints to help someone to lift their limb into a flex position or to lock out the knee so it doesn't buckle, to provide extra support in what used to be just bracing. But this is basically smart bracing now. And so there's even a spin-out company from Harvard that has designed pants, basically, that have some textiles inside the pants that have a little bit of a reel on them, so it can tension the front of the pants or the back of the pants at specific joint areas to provide just a little bit of extra torque about the knee or about the hip to assist people to walk or to run. So there's people then, of course, who think, well, you're providing super strength to them. Potentially, yes, you can do that. But the design for this is specifically suited towards people who are learning to walk again after an injury, or full exoskeletons are these big devices that help to hold the human up and to walk again, with the idea that you can kind of back off the control and let the human take control. But then these sort of devices are just things that may be augmented to what the human already knows how to do. So maybe for an ergonomic situation where I'm loading boxes onto a truck all day, I just need a little bit of extra back support to make that work. Or I'm taking things up and down stairs, and I'm going to fatigue if I'm carrying that load up and down the stairs so much. So I have a little bit of knee assistance to help me propel up the stairs. These are the applications that these designers have in mind. So if you have these sort of situations, you still need to know, what does a human want to do, instead of just, here's a thing, you sit on top of it, and it drives you to the top of the stairs. I mean, that could be fun, but maybe the stairs. So you want the control system to work on its own, but you want it to know what the human wants it to do, so that the human's not out of control. Does this make sense? The distinction? Somewhat? Okay. And then this is an example of a fully powered device. This is an iWalk kind of Biomechanics, it's called. It's a spin out from MIT. This is probably, I think, the first to market in the US for a fully powered prosthetic foot. And essentially, this is something where You can walk on it in a passive, you free same foot design as the previous shown passive element. But inside of this, then, is also a spring element and a motor in series. And so you can compress some energy into that spring at heel strike, and then you can also drive back through that spring or in series with that spring, almost like you would with your Achilles tendon with the muscular contraction to drive the heel off the ground and drive the foot into the ground to propel yourself off. So this is a very clever design. It's packaged pretty well. It's pretty heavy, about the same mass as the actual anatomical segment. So if you were to take your leg and just kind of separate that part and weigh it, it's about the same mass. But the thing is, it doesn't quite produce the same energy that you do with your muscles. So it still feels too heavy to the person who's using it. But in order to do all the things the designer wants it to do, requires a lot of massive elements to be inside of that. And also the batteries go out very quickly on this because it is an actual drive. It's driving. So if you walk very aggressively or very quickly with this, it will push more and more. Just talking about, I use the same battery all the time. So we've tested these with some amputee subjects in real life situations with dead weight hanging from their leg, and then they hate it. And they don't like switching the batteries. I think the last I checked, these were about $30,000 US. So you can see that not very many people have them, probably, because they could instead feed their children or afford to pay rent on their house or something. Most of these devices, all the ones we've been reviewing, they haven't been tested necessarily in a fully ecologic environment, meaning like your real world, real life environment. They're tested in laboratories, they're tested in confined clinical spaces. If the person is allowed to go outside to test them, it's not rigorously tested in a way of how can you control this device. It's more of a wear test. So let us know when it breaks, to break with a nice data point. If it takes 4 weeks to break, and we're doing better. It's that sort of data collection that's going on. He's wanting to predict what human intent is in an environment that we call ecological. So this is a natural environment with the minimization of the sensor necessary to drive it. And he's very interested in machine learning, as we are every time there is, because there's more toys mathematically to be used every year. And when Deepak was in our lab, oftentimes we would talk about how that was last year's machine learning algorithm. Let's not use that. We use a new one. It's more exciting. And so this is one of those students who's very excited about it. So you can see we're not talking about designing a new prosthetic. We're talking about how to use the prosthetic smartly. So this is the first machine learning approach. It's called a beta process auto-regressive hidden Markov model. So it's a bit of a mouthful. There's actually 3 components. And then the second machine learning approach that we're using is a long short-term memory network. So it's kind of a strange name as well, because all have different. It stores it for a little while. When you see that again, it can remember what to do about that. It takes a longer time to train, predicting future events in a cyclic pattern. So what we end up doing is I'll show you just a bit. We take the last 2 or 3 steps before the current time to predict what the next step is going to be. And so this structure is very good for that. The instrument, an average graduate student, essentially. So all of our grad student friends came to the lab to get tested. Not a very representative sample, especially of amputees. But this ion measuring system is an IMU from New Zealand that has the 9-axis system. So it has 3 accelerometers, 3 ray gyros, and 3 magnetometers. Incidentally, we can certify a model just taking one of the samples. And then this shoe here is called a load sole. It's made by Novell, which makes one of the pressure relevant elements to give you a normal force, which for the most part is our vertical ground reaction force. Of course, it doesn't have the capacity to record shear, so it can't give us anterior posterior or medial lateral shear, but for the function of understanding the ground reaction force from the vertical. These devices here, the current ones we are using, are fairly expensive for being just accelerometers and ray gyros, because they're packaged in a very small, tight, waterproof case. And so in Oregon, it's very important or in Delhi, I guess yesterday, we heard it rain a lot, right? If you go for a walk or a run and your sensors get fried because they're wet, that doesn't help us very much. So we pay a lot for these. In US dollars, these are about $800 per sensor per package. So it's not something that you just freely give away to your subjects. So $1,200 US per pair. So more expensive than they should be, in our opinion. But again, less expensive than the full motion capture system. So they sample at different rates, so we have to synchronize those, which doesn't end up being too much of a trouble. And then, real quick, what we use these for then, the load sole we're really only using for event detection as a gold standard, so the ground truth.
For different kind of slides, you need to buy a separate load sole.
Yes.
Nah.
Yes. The question is about, so we bought 3 different sizes. And some of them are a little too small for the person. Some of them are a little too large. So we err on the side of too small because we think if the toes are hanging off the end, maybe they don't contribute too much extra weight or convey the force very much. So it's a compromise to be made. And it's unlike the pressure sensors I showed you yesterday that can be trimmed to the right. These are size 9, size 10 sort of arrangements. And they have all sizes, but they, yeah. So it's a bit of a compromise. What we ended up doing in this case is we bought these because we wanted to take our study outdoors. Really, at first we were doing everything on our treadmill inside the lab. And then with that, it's easy to detect gait events, to say, I know that's a heel strike, I know that's a toe off, because the ground reaction force data tells me that, or video record tells me that. But once we go outdoors, we didn't have that luxury anymore. So then we decided to purchase these to just get gait event detection, which you could probably get from other sources, but we wanted that to be a ground truth that we could base our predictions off of. This takes a little bit of describing. We did a series of trials where the person had an average walking speed from 1.3, or average locomotion speed, 1.3 to 3 meters per second. So 1.3 is right about the average adult human's walking speed. Sometimes it varies from like 1.1 to 2.2 meters per second. That's the transition speed to running. It's very uncomfortable to walk at that speed, and it's very uncomfortable to run at that speed. We'll walk up to that speed and then situation and run faster than 2.2. And then 3.0 meters per second is a fairly comfortable running pace for most anybody. You might not, if you're not in great shape, you might not do it all day, but you can probably do it from here to the guest house. Maybe stopping twice. For a brief rest. And then what we did is we set up a course that was basically just a 90-meter straight course and said you need to get from here to that spot in a certain amount of time. And what that forced the person to do is to choose, essentially, if we give them this distance and give them a time, on average, they're going to be conveying themselves at this speed. But it's up to them to choose how they do it. And so we would tell them, we need you to do a combination of things. We need you to walk at least twice. We need you to run at least twice. But you still need to get to that mark by this time. And so then this forces the person to utilize basically a variety of range of speeds to achieve a real-world task. Like, I need to get to the bus stop by this time. I'm late, I'm going to run. I realize I'm out of shape, I have more time, I'm going to walk for a bit. Oh no, the bus is coming, I have to run again. Right? So you have these natural transitions that occur that are less constrained than what we do in the laboratory. So this came from a group at Ohio State University. I guess his first name, Manoj Srinivasan, is the faculty member there at the Ohio State University who's been doing this sort of work for a long time. He's very interested in the reasons why humans change their adaptation to different tasks. And so he sets up these kind of time constraints and distance constraints, but then tells them you can walk and run freely, change as often as you want, and then he analyzes the metabolics, the energetics, and why they choose to do what they do. So we adopted those protocols. So I was talking about what we get from the load sole, but from the view, we end up only taking the angular velocity, but that's the only channel, 9 channels. And this is chosen based on at 500. So most of the time we want to increase the data points we have, right, for higher resolution. Embed that in the shoe, embed that in the prosthesis. So right now, we'd love to get all the data we can. but we're trying to find to the minimum, which again is a unique challenge. So we tried at first to go to 10 hertz because we just thought, let's go as far as we think we can. And we got no results from our interpretations for that, or not interpretable results. And then we bumped it up by 5 until we found this 25 hertz, we could get repeatedly predictive outcomes. So we were happy with that. We tried then to bump to 50 hertz, let's say, and we got no improvement. So we decided to bump it back down to 25 as kind of a best minimum for us. Okay, so real briefly, we can talk about this perhaps later in the hallway. I don't want to disrupt your sleep too much here. But the beta process approach is depicted by this diagram here. Essentially what it is it builds independently a set of features that are not constrained by the user telling features I'm interested in. It depicts as mathematical features. So it basically puts out a set of derived states. And then the autoregressive and the hidden Markov model portion takes that independent set of features and determines what's the probability that I'm going to move these things from one condition state to another condition state. So for that, we do tell it, we're thinking there might be 2 or 3 things you might be looking for in here. Reduce your feature set down to something that's more predictive. System in this diagram approach in these blue markations here. And so you can see that it's either a 2 or something else. It's not on a continuum. And so it jumps from one state to another state and temporally makes it quite strange to look at. And if you recall, this is at 25 hertz, right? So it makes these really large jumps. So when we first looked at it, we weren't happy at all about this because we thought we like smooth data. We don't like jumpy data. But then when we started seeing there's distinct patterns that jump out having to do with where angular velocity is. And if we know basically where the ground truth of gate events for foot contact and toe off are, then we can start looking at cyclic behavior and see where the states are occurring and for how long. So this is a case where there were 3 running strides here on the 1 foot, and then it moved to a transition step where I'm running, and then I make 1 smaller, slower step, and then I'm walking. Okay, so this is fairly typical for how people do this. If they're running at a relatively slow pace, you can change to a walk within about 1 or 2 steps. And then after that, those 3 walking conditions. So with that definition, you can see a couple things. Temporally, they take less time to get through. Maybe nothing real different looking about this. But then in walking right away, there's a stretch in the temporal distance. So I go from a run to a transition to the first walk, to a longer walk, to a longer walk. And then it stays like this consistently for the next probably 100 steps. So you can see there's a little bit of temporal difference between them. But the thing to note is this pattern of the states tends to stay regardless whether it's running or it's walking. But what you do see is the duration of these states changes for those to match the duration of the angular velocity change. So we start looking at that as not just say where the states are, but how long that state is kept in the prediction. And that can give us some idea about when the transition is about to occur. A different set of state outputs from what we've seen so far. So if we look at the average state duration from the previous slide, how long this state was on essentially. 6, it's a little bit light, sorry, on the screens, it's hard to see. But in the transition from walking to running, interestingly, we found kind of some variety of what's going on in the length of states between those. But then when the transition occurs, they all have this inflection point, but then it goes flat afterwards. And so we looked at this spot and said there might be something here that can build into a heuristic to make like a rules-based switching command. So we see, first of all, that in general, there's a decrease in the duration of the states leading up to that transition, and then a flattening out of that state duration. So we thought to ourselves, this is a discernible pattern. Maybe it takes a while to see it, but we thought, I think this will happen time and time again. What we found, though, in the run-to-walk transition was quite a bit more variety. So very hard to say exactly what's going on here. Is this an increase in duration? It's not flatlined afterwards. Some of the states decrease, some of them stay the same. And so it's a little bit more convoluted or less able to adjust the state predictions in the model. So this is the same data you saw before, angular velocity, black, state, the information in blue. And what we see from the long short-term memory approach is that these transitions occur not very frequently, so this is a good approach to hold that long-term memory. And what we end up doing is, if we want to target one particular stride to guess what its state is going to be, we use the state and the information from the past 3 steps. So in this case, we're targeting this one and using the data from these 3 to drive the prediction. So we would do the same thing then going forward for each of these. So you see then that this, if you remember from the past slides, this was the transition step. So in this case, we take the pick, there's a transition about to occur. And then considering the path, these include pre-transition, transition, first walk, then we're sure it's going to be a next walk. So we get more and more probability that we're right at this point, correct? In the training of this system, we were getting results of 99.5% accuracy. So it's the same basically that the data is consistent enough that even the training marks are showing really high fit. When we validated it with the remainder of the data held for validation, we're similarly getting 99.5% accuracy, which we never see these numbers. So we were really shocked by this. And then when we tested it on a data, it drops a little bit down to 99%. Usually we are happy to get to 95% first, and then try to build it up to maybe 90% as a goal standard. Debug to occur, we saw 100% accuracy. So this is interesting, maybe not walking trajectory. If I mispredict that the next step is still going to be a walk, like half is a little bit for its stiffness. But if I miss the transition, then it's more critical. So if I'm walking and I go to run, but the foot doesn't know I'm about to run, it doesn't know what to do, then I'm likely to stumble. And so we think this is more important even than knowing what the steady state predictions are. So this allows us then to build a little bit more of a weighting function into our approach to say the heuristics predict that you're about to make a transition. That's more important than even knowing what the speed of your transition is going to be. It's more to know that the current state of walk is going to change and just be ready for the next thing. And then if we know the next thing is likely to be a run with another layer of that heuristic level, then we can say, likely you need this stiffness because the first step of every running step, the first step of every running event has this required stiffness to be able to propel. So our next step is then to build this basically into a system that allows the variable stiffness foot that Peter has been designing in Wisconsin to change the stiffness profiles of that foot in real time. So we can test it out on an actual human using that device to see if this approach can allow us to predict what's going to happen and give them basically full freedom in walking and running transitions. So the goals here, we have different reasons to use these devices. This is an above-knee amputee with basically the latest devices from Vanderbilt that have knee and ankle function within them, a person to use. An above-knee situation requires more help anyway. And then we also want, though, to get to this point where the person can change a walking situation to a running situation without having to change out the gadgets that are attached to their foot. So this was our purpose, basically a restatement of what we said before. We're happy to show that we had some good accuracy. This, by notes to the literature, is better than basically anything else out in the literature in this case, and better than our own work in the laboratory as well, which we're quite surprised about. So in general, we do this when we find these sort of answers. So sometimes there's more of us to do this, but most of the time it's just one person. Lumberjack shirts. I don't know why they look the same. I can't tell them apart. So they're working on a project where Peter and I have been working on this foot here. And in fact, we have a patent pending in the US that maybe in a year hopefully will be. It's a relatively simple design where we take a running specific foot. However, we need to know when GIAN is working on that has a variable stiffness option within it. Research talk at this point, you can take any questions or any open discussion about the project. I know Deepak has something about that.
So regarding the number of movements,
But generally we try to let it, so it's like almost an overhandling of the data. But it provides its own state quality of those patients.
You have used unnamed shoes for data collection, right?
Yes.
Is it subject specific or use the same shoe for all the subjects?
The study we used the same shoe for all the subjects, type of shoe,
Yeah,
not exactly the same pair. And so the second part of your question is often for free shoes. So we can control the footwear in our studies, and they're generally happy to help us with that. We do find that it's a big change in the way that the transitions may change the angular velocity profile a little bit, but the overall trend is the same. It may have a higher magnitude at one point that's a little bit earlier, or transition a little bit more. But it seems like an idea. And then, yeah. But here, we think we're capturing basically the bulk of what motion is, and that most of the changes that would occur with a different type of shoe would be back in here with compression, or in this space with how they're pushing off heel to toe for traditional running shoe from Nike. But if you then wear a raised heel of any sort, that will just change the orientation of the foot at contact and toe off. So I think the overall angular velocity pattern may be somewhat the same, but it will be biased towards a more vertical plantar flex foot. Does that address your question a little bit? Yeah. It's a good point for sure.
So may I know the response time that your system takes?
How long does it take to train it, or?
From the time it takes a particular increase and the.
Okay, good. That's a good question. So we consider that question important at two stages. One is once we have the data, how long does it take to train the model to give you bars about 50 to 70 milliseconds before the next heel strike. So during swing processor, it will be analyze this data to just make a very quick decision about the next averages about at that range. The variation is maybe 10 milliseconds either side. Yeah, so it's very close.
Sir, have you worked on any augmented device?
Any which?
Augmented. All these are for augmentative application, right?
Right, augmented. We have not. We've talked about that this control algorithm can be used for the augmented, like the exosuit exoskeleton, as a way to help their controller. But we have a few friends who are working in that space, and we've been telling them we have a nice approach that maybe they want to use, but we have.
So in the long short-term memory network, you said that you were using past 3 steps to predict the next step, and then it functions. So in the slide that you were showing, there were 3 walking, 1 transition, and then the running. Right.
So this is actually so the entire basically run this 3-stride prediction stride throughout all of the strides of that data set. And so it continually runs through that whole data set. Does that answer your question?
That is just one part of the
Okay, one part.
So how good is this prediction? I mean, is it actually 99% accurate in the real life scenario as well? Because like let's say I'm wearing one of those devices,
yeah,
and I see like I'm walking. I see my bus is there. I'm just about to run. So there's a transition phase from walking to running. And then I see that okay, the bus is going, so there's no point of running. Then I can slow down. So then the device will be reading that okay, he's transitioning, so next he'll be running. But then I do not run.
Right.
How does it predict that?
So in those transition cycles that we had, people were transitioning from walk to run and back to walk and to run and back to walk multiple times during that time, and it predicts all of those transitions. So it's still not real world. Yeah, it's still a confined space, like a constrained approach. But our hope is we showed we could do this same approach in the lab. Now we're showing we can bring them back in an hour or something, and maybe put it back through the data, run the system through, and say, this makes sense that it failed here because look, they went upstairs. We didn't have it designed for that. It made sense that it failed here because they came to a sudden stop instead of a transition to a rails before we even ask an amputee to use it. And then our next goal after that is to try this out on the amputee, actually to get them walking on our treadmill first in their own standard prosthesis and have the activated prosthesis sitting on the bench, changing its fulcrum in response real time to what they're doing. So we can test that first and then put it on the treadmill and put it on for overground walking and then follow them around and ask them to just do things while we record what's going on. So it's a multi-stage project for sure.
So this is quite a bit far away from the real world application.
Far from the original application? I don't know if I
original application, but like when you can release it into the market as a product.
Oh, I see. Yeah, so the release to the product, we have a hard time predicting, always. So this particular device, at the moment, we don't have it in a timeline for release to market. We have, patents pending on it, and potentially if that goes through, then some company will want to license the technology. And with that, at that time, we want to give them both the design of the foot and the controller design as well. So when that happens is really hard to predict. So our goal is to continually show that it's improving more what's going on in the real world environment. So we have the evidence to justify that it's important for that company to license.
And sir, in the next slide where you're showing the device where you have the a person who runs, they tend to incline quite a bit in front, right, if you're running or while running. So won't the contact angles change quite a bit to just, would it actually comply with it, just removing the heel and
Yeah, it could be if we have this heel still locked down, if the person decides to run and leans into that, it could be that this isn't going to have an impact anyway. Yeah. But we want to be very careful about the fact that not everyone transitions into running exactly the same way. Trying to run, starting to jog a little more, just likely to step on the heel or their midfoot. The constraints on prosthesis themselves. What we are interested in is if there's any way to put a heel component in that when they're walking conforms to the shoe as well. And when they're running, lifts up enough or it becomes a passive element so that even if they do strike on the heel, it gives a lot of compliance instead of being a rigid structure like it was before.
So this is not just, it is not a blade that athletes could use for running as well as walking in.
And I just start running. And we want that to be the option that they have.
Not sprinting.
It's a good point. This is not designed for cardiovascular risk goes down. Yeah, it's a good question. Yeah. That's thought as well.
Sir, in this design you had for heel strike. So why not for toe off simultaneously? Why don't we think of toe off as well? Because toe off would be the it is a propulsive phase of the game. So if we are thinking for walking as well as running, so that is also equally important. And
yeah, timing. Is that what you're asking about, or are you asking about the design here?
about the design.
So that has propulsive drive to it, right? So it pushes the person off the ground. The rest of these propulsion side of it, because we think that mechanically it's a much harder and it requires us to put extra power in there and an actual motor drive as well. Whereas all we're doing here is utilizing passive elements and then just changing their conformation before the loading occurs. If you have a cool idea for how we can do that and reduce the power required, we'd love to hear about it. Deepak, you have a question?
I just wanted to have
Oh, I see.
part is like, once you so we decide that this might suit this, running fine for now. It is like multiple tablets. What are the tablets?
Any words like something like that.
I'm not sure I understand the question. Sorry, can you restate?
It's
It's not specifically designed to be biomimetic of birds, but it is a similar structure, perhaps, to their mechanism, right? And so, one interesting opportunity with Peter when we were having our video conferences, our Google chats that we have every 2 weeks about what project we're working on, what's the next step. We were talking about the design between the walking foot and the running foot, and how they're so different, and how we want something that's a relatively easy task to just change the conformation of the foot. And I just take it out of the picture. Wouldn't that do it? Yeah, that's pretty extreme in a way. It's not, still make sure you don't need it. We weren't thinking about in nature what that mimics. So, but are you saying you think this mimics a little bit of foot motion of the birds?
yeah.
Interesting.
My intuition says that it's a little bit like the birds when they have the and
Right.
the designs. Seeing this,
It looks like it, yeah? Okay, that's good. I do wonder if we look at the running fowl, like the guinea fowl or ostrich, or the running conformation, if they the heel section or not. Do you know? That's interesting, yeah. It's a good question.
you showed some prosthetic foot. Does it is this designed to walk backward?
I think that this device would be capable of walking backward. This device I'm a little bit less unsure of. I think if the heel is down, then yes, potentially. And if the heel is down, that means you're not running, I suppose. So if you just want to walk backward, I think that it would be locked down, similar to its walking conformation. And then you have the ability to control the contact with the ground with the shoe interface, compared to maybe this rubber stop here is not sufficient to make this an option in a way that actually maintains stability with the shoe conformation.
The previous one, bionic foot, does it do things like backward walking?
You can do backward walking. It's not the same as what you do with your anatomical ankle, to allow the tibia to roll over the top for a little bit of dorsiflexion. But if I step backwards, it's not going to allow me to change my dorsiflex position before stepping down. So it'll be a 90-degree object that you'd be stepping back onto. So it might be very awkward to force your knee into a hyperextension, but it is possible to do it still. So yeah.
So the data you showed, the machine learning data, is it talk about anything regarding energetics of transition phase?
It doesn't account for that, no, not at the moment. We are looking to analyze the end product of, once we make these changes, what are the energetics of the mechanical system, and also what are the energetic savings when you have actually is more responsive to what the person wants to use. So we've done some of that work in the lab already, not with this particular device, but with similar other devices. And we look at how much energetic cost there is to the joints to still produce the same propulsion necessary to walk. And we can see there's a transfer of energy from an ankle-driven function to a hip-driven function, and back if the prosthetic foot becomes more capable. Whether all of the degrees of freedom, I think the answer is no. It's really just the one degree of freedom of plantar flexion dorsiflexion capability. Specifically, these devices are meant to basically not conform in the frontal plane or to allow any torsion to occur. Specifically, if you walk on these or if you run on these and you have to turn a corner, we may need to conform our foot to still match with the ground but have already a redirection of the rest of our body. These, it's like to then push off of. In one of these blades, they can conform it to the ground with their whole limb. The other end of the spectrum is to go to the brain-computer interface, right? So maybe